Hello, everyone, and welcome to the latest episode of uh, Expert Insights. Today, we've got Alexei and Jack, and we're talking about quantum machine learning for finance. So, while the session is just starting out, uh, have a read at the ticker at the bottom. It says add in hashtag packed to ensure that you win a copy for yourself and you enter the raffle. And yeah, if you have any queries, please feel free to add them in the comments. I can see a lot of people have started adding in comments. Uh, about great. Keep on adding more and more comments to ensure that you are one of the people who gets picked for the ebook. So, welcome, Jack. Welcome, Alexei. How have you been?
Very good, thank you.
Hello, everyone.
Great. So, Alexei, while we are waiting for others to join in and ask their queries, I have one. Why not start with something? And something really basic. Well, there's nothing basic when it comes to quantum, but what do you think? What do you both think are the skill sets that one requires to work with quantum financial modeling in their team?
Well, I would say that physics background would definitely help, but it's not a must. You should
Mhm.
clearly understand that in order to be involved in quantum computing and do some interesting stuff with quantum hardware or maybe on the quantum simulators, one doesn't have to be a physicist, a professional physicist. What is needed probably is some basic programming skills, inevitably, because we want to do some experiments, some numerical experiments. We want to write some programs. What is also needed is some basic understanding of, say, first year mathematics, standard university course on linear algebra or something, vectors, matrices, some basic operations and a lot of interest for the subject. Everything else can be picked up. And it actually a motivation for our book. And today I think we are going to talk often about our book on quantum machine learning and optimization in finance, that someone with a keen interest in quantum computing and quantum machine learning and hopefully in finance as well can pick up basic knowledge of quantum mechanics quite easily, to the extent needed to write first programs, first algorithms to implement first models in quantum computing and quantum machine learning. So I would say um, anyone who had 1 2 years of higher education um, and knows a little bit of programming, ideally in Python, but doesn't have to be Python. And here we can also mention another excellent book by Pact, which I enjoy very much, Python Machine Learning, which would be probably also a good book to have. So our book should come probably together with Python Machine Learning, I would
Mm.
say.
Right. So just to give everyone a heads up, I'll just show you the book that Alexei and Jack have written. This is the book that Alexei and Jack have written, and this is what we are talking about right now. So yeah, I think you've answered one of the questions already, by the way. Sarabjit asks on LinkedIn, which programming language is relevant here? And Alexei, I
Yes,
think you've already mentioned that.
so maybe just to bounce on, on this question and your question, Dishar, just to add
Mhm.
one little thing to mention. So the book originally came because we started teaching a course, Alexei and I, in the MSc Math Finance in Imperial College, where we thought, oh, it would be a good idea to add a course on quantum computing within the program. And so the book and the course was designed for students who have basically a strong background in, I would say, math in general, meaning mathematics, analysis, statistics, extremely important. And we developed the course and the book for that kind of students. And so, in my view, the skills for people in, let's say, quantum finance. I don't think there's a precise terminology or accepted terminology yet, whether it's quantum computing finance, quantum finance, financial quantum. Um, it's in the end, the people will work in finance, so they need to know some finance. They need to know, I would say, the important part, but of course I'm biased being in the math department, but they need to know core math, analysis, statistics, some programming, and
Mhm.
Python is one of the most important languages these days. It's used everywhere, and now there are some very nice Python libraries for quantum computing. And of course, it goes without saying that an interest in the topic, but I, the physics part, in my view, and I say that not coming from physics but coming from math, physics part is less important. It's important as intellectual curiosity to know where things are coming from, but in order to start implementing, let's say, quantum neural network, to
Mhm.
implement them, to understand them, to use them, somehow one does not need really too much physics. Of course, understanding physics is important, uh,
Mhm.
but one needs to know very well, have a good understanding of classical statistics, whether you
Right.
call it machine learning or not, but fundamental core statistics, math, numerical analysis, and programming. And I would say programming here, the most important would be Python. Yeah.
Yeah. So Jack, you actually started answering the next question, and you went back to the first one. So I will put up the second question here. So Houston actually inquired on LinkedIn, what should come first, quantum encryption, even it's just the mathematics of it, or readers trying to figure out working with a quantum computer?
So I would say I'm not a physicist, right? So I'm trying to understand a little bit how hardware works. But for example, if I switch, so if I work in I don't know, a bank or hedge fund implementing quantum algorithms, I'm not going to build the hardware. Right?
Mm.
So I'm not going. I think it's good to understand what superconducting qubits are, what photonics are, and so on. But I'm not on the hardware side. I trust all the people that will build a quantum computer, and but I need to know a bit how that works in the sense that if I develop an algorithm, I need to understand maybe how the qubits are connected on what
Right.
graph they're using to connect that qubits. So I need to know a bit about it. But if really I work on the applied side of it, and quantum finance, for example, then math should come first. Because
Mm.
in the end, you work in finance, everybody uses models, and you have to understand the models that already exist. So the numerical part, the stochastic part of them, in order to improve them or to propose an alternative. If you don't already know the models and how they perform, then
Uh-huh.
then there's a problem, right? You don't want to reinvent the wheel and restart everything from scratch.
Yeah. Right. Fair enough. So there are a lot of comments coming in, and thank you everyone for posting your comments and queries. Keep adding them in, and we will try to get as many as possible answered. So Akila has inquired how this can be integrated with AI.
I think this is great question, and actually, it's the title of our book. Because high performance computing and AI or machine learning, they come together, right? We cannot even start separating them. Inevitably, they have to come together, and we consider it together. So think about quantum computing as any other type of high performance computing. Um, and think about applications, successful applications of machine learning, whether it's discriminative models or generative models or any kind of sophisticated deep neural networks and so on and so on. Everything can be implemented efficiently on quantum hardware. Clearly, algorithms are different because classical computers and quantum computers operate differently. There are massive differences. But in terms of AI, machine learning, absolutely. And I would even say that in quantum computing, there is a whole range of known algorithms, very useful algorithms. Some of them will become productive later on, in 5 years, 10 years, maybe 20 years, we don't know, because they require extremely powerful quantum computers with error correction. So now we simply don't have hardware on which we can run them. At the same time, there is a class of quantum machine learning models or algorithms that can be efficiently executed on existing quantum hardware, which we call NISQ, noisy intermediate scale quantum hardware. Algorithms that are somewhat resistant to noise, where we can have interesting results even on existing noisy small-scale quantum hardware. So I think AI is not only sort of part of the picture and must be integrated into it. It's actually probably the most productive application right now. So all the many models we consider in our book, many algorithms we describe in a very detailed way in our book, actually belong to the class of quantum machine learning algorithms, which we can test either on existing noisy hardware or on efficient quantum simulators.
Maybe just to add one thing.
Yeah, please.
I think there's something. It's very interesting the way the question is phrased, and I think that's important. Is that I don't think quantum should be an alternative to AI or other methods. It's really about integration and quantum computing as a tool. I think there were some questions about it in the chat as a hybrid version. So it's a tool that combined with other classical tools, deep neural network and so on, will actually provide new solutions. And it's really about integration and hybrid system rather than quantum is a completely different thing and completely different path. So,
yeah, Jack, interesting that you would go to answer this one, because this is actually a three-part question. There are three different comments. I'll just read it out to you. The first part asks which frameworks, Qiskit, Bracket, does the book use? Is the second part. So, okay. Which frameworks do we use in the book? Is it Qiskit or Bracket? And then the second part is this. Also, do you look at hybrid, high performance computing plus quantum, or TPU, GPU, and QPU?
So, I mean, on the actual implementation side, so the book is not about, so we, it's not a computer science book, right? So we don't have huge, bits of code in the book. I think at the personal level, when we teach the corresponding course in Imperial, or when for our own research, we use some languages. And now there are actually several competing languages, whether it's Qiskit or Bracket or Penny Lane. There are quite a few which are competing. So I don't want to go into support one or the other. I don't have any shares in any of them, and they're all very performing on their own side. But the book does not really take sides on which language for what, because
Yeah, it is currently language agnostic.
yes.
So there is an interesting question by someone on YouTube, in fact. They are developing a machine learning model development in finance to forecast future analysis product. How much is this book usable for them?
Alexei, do you
Well, I would say that at the moment when we do experiments with various ML models, inevitably all these models, all these use cases, they deal with relatively small-scale problems. Partially because existing quantum hardware, NISQ hardware, has at most 100 qubits. I think recent development actually went above 100 qubits, but most quantum chips we can have access to has about 100 qubits. And quantum simulators, obviously, being classical, cannot simulate more than, say, 50, 60 qubits. Then we start running out of memory. So we can experiment on the very wide range of very interesting problems, but they are still experiments because they're small scale. And it's important to understand this. It's not about sort of productionizing algorithms and tools right now and start solving big scale problems for a lot of data, and that would require hundreds, thousands, maybe millions of qubits. We are not there yet. We are at the stage when we can test a wide range of algorithms on very interesting problems, and there are a lot of interesting problems which we can formulate in a way that can be addressed by tools of quantum machine learning. But I think it's too early to try and to sort of embed quantum computing into sort of day-to-day business processes.
Yeah, maybe to add one little thing there, even if you look on the, let's call it classical machine learning or classical neural networks, suppose you try to do classification problem, which you can ask the question to both academics and practitioners, which neural network is the best? Should you have 5 layers, 10 layers, 20 nodes, 100 nodes? You can do that in the comment in the chat. I'm pretty sure everyone will have a different answer. Why? Because we have of course a much better understanding now, but not full understanding. And I think quantum neural network, we have a similar, we could say, type of problems, which is how expressive are they? So expressive in the sense, what kind of complex functions or complex problems are we able to express with the quantum neural networks? So we have very similar questions, actually. So even for small scale problems, there are questions that we can say, oh yes, I'm going to have a classical neural networks with 100 layers and 200 nodes, but then it becomes untrainable. So we will have a smaller one, but what's the best one? And the quantum neural network side, we have actually very similar questions, and there's a very nice correspondence between the classical neural networks and quantum neural networks, which still needs to be understood precisely. So in the end, depending on your, I would say, application and what you want to exactly use it for, some quantum neural network can actually be extremely useful as classical machine learning. Of course, if your problem is extremely high, high dimension, the quantum hardware, quantum technology is not there yet. But for a smaller scale problem, we already have a certain number of tools that are quite powerful.
Nice. But it is a good start if you go to see, because quantum is only getting stronger. So FilmZale actually has a query on LinkedIn. What are the intermediate use cases of quantum in retail banks at the moment?
Well, I would say that the whole range of discriminative models, classifiers, it can be as simple as credit decisions. Should we extend a credit to a particular customer, or should we not? All sorts of binary decisions are very natural in this regard. Even very simple quantum neural networks can be trained very efficiently, and actually on reasonably large data sets with a reasonably large number of features. It doesn't have to be a binary classification problem. It can be multi-class classification problem, still works, and it can be efficiently trained. So I would say any kind of well-specified, well-defined classification problem places advantage of quantum neural network in retail space. For, say, investment banks, for quants working with traders, and dealing with complex mathematical models, complex problems. Maybe generative models would be better. For example, market generators, the ability to generate synthetic market data with desired characteristics, because as Jack mentioned, there is a lot of research going on how to measure and estimate expressive power of quantum neural networks relative to classical neural networks. And we know already that there are theoretical results stating that quantum neural networks have exponentially larger expressive power in comparison with classical ones, comparable classical neural networks. So it means that we can learn very complex distributions. We can encode very complex probability distributions in the state of this tiny quantum mechanical system, from which we can generate samples. By measuring the state, we would generate samples from the encoded probability distribution. And in investment banking space, when we have problems of running all sorts of Monte Carlo simulation, or generally generating a lot of synthetic data, synthetic market data, then powerful generative model would be very useful. And here we also see big potential for generative QML models.
So, Alexei, it's quite good to hear that you can work with a lot of complex problems with quantum and quantum machine learning. What about the accuracy levels? How is it better, or how does it compare when you take traditional machine learning versus quantum machine learning?
This is a great question, and this is why in our book we always provide classical benchmarks. In our book, we cover the whole range of models: discriminative, generative. We have optimization problems, and every time we use either actual quantum hardware or a quantum simulator. We run experiments, we produce results, we measure performance. We always provide a classical benchmark. We always specify the most suitable equivalent classical machine learning model or classical optimization algorithm, and we measure performance of both on the same problem with the same input. And what we know is that as long as problems are relatively small in size, QML models perform at least as good as classical models. Sometimes we can see some first signs of emerging quantum advantage. For example, in some cases we can detect noticeable quantum speedup if we ignore all sorts of overheads. But the transition to large-scale problems will have to wait until we sort of catch up on technological development on hardware side. But from purely sort of computational, mathematical, if you wish, or computer science point of view, we do demonstrate that QML performs at least as well as classical ML.
Okay. All right. So I think, Jack, you can take this one. We are almost on track to answer the second question, because we were talking about optimization and the significant advantages. So Dan on YouTube has inquired, can you give an example of finance problem where quantum computation at the current level of hardware implementation would provide a significant advantage?
Yes. So maybe just one little thing. There are two, problems or tools, right? One is machine learning and one is optimization. And the two are kind of very different objects. So what we're saying about, not yet in production, I think this is true for quantum machine learning. The quantum optimization, there are already some success stories at, for a high dimensional problem. D-Wave, for example, has been around for actually a long time and has solved, so I would say very few in finance so far, but quite a few in other industries, large dimensional problems. with actually very good results. So of course we are focusing on the finance side here, but we might and we should actually learn from other success stories in other industries, especially on the quantum optimization side, on quantum annealing side. So right now, so to answer, this particular question about the current level of hardware implementation, so I would say optimization actually could provide an advantage. So I think it depends on what kind of optimization. Portfolio optimization, simple portfolio optimization could be, but we have actually very powerful tools already. My feeling is at the current level, it's mostly on the quantum machine learning side. And I would say and there's still not a complete agreement, but that quantum neural networks provide a lot more expressivity than classical neural networks, even on a small scale thing. So, for example, when it comes to so there's a branch of quantitative finance these days about pricing and calibration of stochastic models using deep learning algorithms. And for these, you don't need actually very deep neural networks with just a couple of layers and not too many nodes seem to be sufficient. And so for this, for example, I believe that quantum neural networks would provide actually a very strong alternative, because they seem to provide a lot more expressivity. That said, there's no clear result yet. It's a big area of research these days, and I think that's what the book aims at looking at, which is to provide the content, to provide the background, and some directions for this to actually be studied more.
So let's come back to LinkedIn, and Hitesh has a good question over here. Which is an effective tool to amalgamate quantum computing with neural networks in terms of hardware and software? And what is the recommendation of it?
Jack mentioned many quantum SDKs, Qiskit, Bracket, we can mention Forest, and many others. In our book, we always stress that we don't have preference for any quantum software or any quantum hardware. We don't try to predict who is going to be the eventual winner. Which tool is better. It's a matter of taste a little bit. However, I would say that to probably to some extent, Qiskit is one of the most popular tools. And even in our book, when we mention numerical results, very often we obtain these results by running experiments on quantum simulators using Qiskit. So on Qiskit quantum simulators, using programs with Qiskit formalism and so on. So and here I think I cannot I cannot not to mention yet another book published by PACT, The Dancing with Qubits by Rob Sata, which is also an excellent introduction to quantum computing. So I think if you want to have like full range of books looking at this subject from different angles, but converging in this point of quantum computing, neural networks, machine learning, then it would be probably Dancing with Qubit by Rob Sata. It would be Python Machine Learning by Sebastian Rashka, and our book, of course.
Right. I think this is a query that we're going to get time and again. What are the tools and components used in this book? And I think it would be a good thing to clarify it for everyone.
So on the math side, fundamentally most of the book is the book, if you have a decent undergraduate in math, you can read the book. And actually, the first chapter records all the tools you need. So the book is really self-contained. So on the math side, it's really mostly linear algebra. On the programming side, if we mostly so in the application we use Qiskit, and then the rest is so optimization, which is basic, I would say, basic optimization. So least square regression and that kind of problems. Neural networks. Again, we call the basics of neural networks, but in order to understand that, you don't need a PhD in math. So there's really, on the math quantitative side, a good background in general math or physics. Of course, some knowledge of finance can be useful if you want to understand a bit more. But again, the book is self-contained, so I think we explain that properly. And on the quantum computing side, so there are bits, a bit about the quantum hardware, for example, or how do you map your problem to a particular graph of quantum hardware. But all this is actually explained in the book. So, yeah.
And does the book cover Monte Carlo simulations? While we're talking about knowledge.
So the title of the book is Quantum Machine Learning and Optimization in Finance. Right. So it does not mention Monte Carlo. It does not mention the kind of, I would say, classical quantum algorithms like quantum Fourier transform, quantum phase estimation. The reason is that there are already some very good books on, for example, quantum information theory, about classical, I would say, quantum algorithms. We added a final chapter with a bit of quantum Monte Carlo, actually. So this is covered, but I would say this is not the main focus of the book. The reason is that we believe that quantum Monte Carlo, for example, even though theoretically there's a clear speed up, and we highlight it in this chapter, in the final chapter, the technology is not there yet to really benefit from it. So yes, it's covered. We provided the mathematics. So actually, this chapter is a bit more math technical than some others, but we provide the details, but we do not look at the actual application and the practical side of it. It's kind of an overture, if you wish, to what if we had an actual full quantum computer.
Okay, there is another follow-up, and so both, I'll quickly answer this for you. You can head on to Amazon, our website, Pact, or mobile app. Okay, you can have a look at all of these places, and you will find my book. So, and so there is a question from Omkar, and can you give some examples in finance where quantum annealers have advantage over classical algorithms?
Probably I can start answering this question. In our book, in chapter number 3, we look at one particular use case, which is a discrete portfolio optimization, a very well-known NP-hard combinatorial optimization problem, which is a hard problem for classical computers, but appears to be very natural. It lends itself naturally to be addressed with quantum annealing. It can be formulated as a QBA problem, quadratic and constrained binary optimization problem, which is exactly the type of problems solvable on quantum annealers. And our results, our numerical results, our experiments, actual quantum hardware on D-Wave 2000Q quantum annealer demonstrate 2 to 3 orders of magnitude quantum speedup relative to equivalent classical approach. However, we should also remember that it's very hard to to provide direct comparison between classical computers and quantum computers, because these computers have different overheads in terms of how data is stored, extracted, processed. But if you concentrate only on computation, on purely computational part, then results that were obtained actually 4 years ago already demonstrated 2 to 3 orders of magnitude speed up, quantum speed up. Since then, D-Wave released a new quantum chip. They moved from old Chimera graph to new Pegasus graph with much better connectivity, with lower noise, better controls. So I think it shows us a direction of travel. Even 4 years ago, from purely computational perspective, we demonstrated experimentally material quantum speed up. I'm sure that if we would run the same experiment now on the new chip, we would probably add another order of magnitude quantum speed up, and who knows what will happen in the next 3 to 5 years. So I think my main message is that let's look at the direction of travel. And we notice material improvements in quantum hardware every year. Every year, if not every month, we have some breakthroughs, sometimes minor, sometimes major, but it always moves in the same direction. So what was 2 to 3 orders of magnitude quantum speed up a few years ago will be absolutely sort of amazing just a few short years from now.
Mm. And I think there's an important question over here by Bita as well. How much of your book can help the researchers to deal with the problem of covariance, matrix estimation, and portfolio optimization? Would you like to take the lead?
So, okay, I can say one thing, but Alexei knows this topic better than I do. To me, the quantum part really is for the optimization side, where, as we said, quantum annealing, for example, brings something. Covariance matrix estimation, I don't see the quantum part there. And I would say one reason is we haven't really touched upon that yet, but one big bottleneck about with quantum computing yet, as much as I support quantum computing, of course, is to encode classical data into quantum data. And this is a bottleneck. So covariance matrix estimation, building a covariance matrix from data, this can be done very efficiently using classical tools, and this is not too hard. The quantum part will really benefit the actual optimization side of the problem.
Yeah, and I also would like to mention one model described in our book, which is quantum semi-definite programming, that doesn't deal directly with the covariance matrix estimation, right? Because the way we construct covariance matrix from the underlying financial data, typically from some time series, is well defined, and I think it is not a problem to build the covariance matrix. However, the biggest problem in portfolio optimization is instability of covariance matrix. Sometimes a small noise around estimator of covariance matrix would result in totally different optimal portfolio. So there is a task of performing first, robust portfolio construction, and secondly, maximum risk analysis on covariance matrix. And both these problems can be efficiently addressed with a tool called quantum semi-definite programming. And this is very well described in our book. So we have the whole section on quantum semi-definite programming.
Alexei and Jack, before we move ahead, I think we are way past the halfway mark. We should actually do at least a first giveaway, and it would be a shame if we don't do that and do both of them together. So let's do our first one first. As you can see, there are 49 people who entered the draw. And yeah, I'll just go ahead and click the draw. So this is randomly doing it. My hands are here. I'm not the one picking it. So Thomas Nee is the first winner. Congratulations, Thomas.
Congratulations.
As you can see your name on the screen. So if you can just contact me on LinkedIn, just drop me a message on LinkedIn, and I'll be more than happy to organize your e-copy for you. Congratulations, Thomas. We'll come back to it towards the end where we pick the second winner. If yeah, please continue adding your messages and into the raffle, and we'll do that later. So there is an interesting query here by Raphael, and Raphael inquires, "What are your thoughts about interceptions between? Is that interceptions? Yeah, interceptions between quantum machine learning in finance, quantum economy, seen from the David Earl point of view, and quantum finance."
Yes. So, okay, maybe I can start with that, but so first of all, as we mentioned in the beginning, I don't think there's a clear terminology yet as to what quantum finance means, or whether it's quantum finance, quantum computing in finance, financial quantum. There's a whole mishmash of words. So the the quantum finance book by Bilal Baki. So this is, if I remember correctly, this is about quantum field theory applied to finance, which is, in my view, completely different from quantum computing. Of course, there's a common background about quantum mechanics, but this is actually a very different take, and it's not really about computing. Quantum computing, as the word suggests, is about computing. Uh, the other one, the quantum economy, I haven't read it yet, so that I can't say much. But maybe Alexei has.
I agree with Jack. I think we have to be very careful when we deal with this new emerging terminology. And to me, quantum finance actually relates not to quantum computing, or definitely doesn't relate to computation. It's maybe related to application of well-established physical models in a different context. To economy, to complex systems, um, sort of quite orthogonal to what our book covers.
Yeah.
Okay. So we've almost answered quite a few queries in the comments. So if you have any more, please feel free to add. Until we do that, let me ask one of the queries that I have in my mind. So, Alexi, Jack, feel free to answer this, whoever would like to pick this up. What is the best approach for an organization looking to test the water with quantum financial modeling? What should be the best approach for them?
So, no, Alex, you go.
Yeah, go on, Jack.
Okay.
I think it's a story of my life, right? Because I was actually part of an organization at my previous place, which was Standard Chartered Bank. We actually faced exactly the same dilemma, if you wish, given a lot of interest to quantum computing and understanding of the potential of quantum computing. How would a big organization, large international bank, deal with this? How can we get involved, and what should we do? And the answer was, I think, quite universal and applicable across industries and across businesses, large and small. First, we need to understand that we cannot afford to do nothing, right? We just cannot wait for 10 years until quantum hardware matures, and then start playing the catch-up game, hiring very expensive consultants and paying for expensive platforms, expensive systems, and generally being left behind. It's much better to join an emerging quantum computing ecosystem as an equal partner. Because whether business is large or small doesn't really matter as long as this business can bring interesting use cases. And what we collectively discovered was the fact that quantum hardware manufacturers and quantum software development companies, they're very much interested in interesting, practical, real-world use cases. And it's not it doesn't require a lot of investment. Sometimes it doesn't require any investment to actually join forces with academic institutions, with quantum hardware manufacturers, with quantum software development companies, in order to build models, to test models on real-world practical use cases, do classical benchmarking, provide feedback, see how it can potentially be integrated in business processes, maybe not now, but several years down the line. And I think this is a way to get involved. And I think companies who are not doing this, they're definitely missing big time, because there is a very clear and very material first mover advantage. And I think it's worth remembering the stories of classical digital computing, which emerged in 1950s, then internet, which emerged in 1990s, and we can actually see who benefited most, and we can potentially even quantify the first mover advantage here. So I think it would definitely be a shame not to get involved at this stage, very early in the game.
Yeah, so just to add up on this, I think there's a difference now and 5 years ago, 6 years ago. I would say 5-6 years ago, Alexei was pretty much the only one in a bank doing quantum-related computations, let's say. I think now there is at least general understanding that there is a new technology with hardware, not full hardware yet, but some hardware, which might bring some clear advantage. And I think there's a clear understanding there. And in fact, over the past couple of years, most major banks have appointed a couple of people as head of quantum computing or developing an internal quantum computing group, where the goal is basically to develop some use cases and to see how they perform compared to classical technologies. And I mean, now, pulling the blanket a bit towards me, I think there's clearly something to do. Alexei mentioned it as more interaction between companies and academia. And so, for example, we have strong students who know math, who know statistics, who can code very well, and who actually know the basics of quantum computing, who can actually spend 6 months in a company implementing some use case, implementing a quantum neural network for classification, implementing a quantum annealing tool for optimization. So I think one way to do it, I understand that a company is not going to hire 10 people full time to switch everything to quantum production, right? But to develop some use cases, to have more partnerships actually with academia, and with, of course, with the quantum computing companies, to start building and ensure that really the technology is already there, or part of it is already there, and we can already build some use cases.
Right. So I received a question from a colleague of mine internally. So let me do one thing. Let me post it here and then share it on screen so that everyone can see it there. So yeah. So how do noisy intermediate scale quantum computers make quantum modeling more accessible?
Maybe I will start answering this question. We already touched on this point. NISQ computers sort of prevent us from running some what we call classical quantum algorithms, because for factorization problem and some search problems, we need much higher quality quantum hardware. But NISQ computers can be used for experiments on a number of quantum machine learning problems, which because there are some algorithms, some methods which are somewhat resistant to noise. And in our book, we look at several such methods, such algorithms. One is variational quantum eigensolver, and to some extent, even quantum neural networks are noise resistant. In some cases, one can argue that some residual noise present in quantum hardware plays the same role as artificially injected noise in classical machine learning when we add noise when we train quantum neural network in order to prevent overfitting and improve convergence. So I think right now we are trying to play to the strengths of quantum hardware. So I think we can probably reformulate the statement, this question. It's not that NISQ computers help us to do something. It's that we deliberately choose problems, use cases that are solvable, or problems that can be run on NISQ computers. So we're trying to play to the strengths of the hardware.
Okay. So let's take one last query because I can't see any more, and then we'll do our final draw. So, Alexei, Jack, do you want to take this up? Will quantum computing bring an end to internet security?
Sure. Well, sure. Happy to take it. Not sure as the answer. No, that's my answer. And I mean, the reason is, you could say, if code breaker have a very high performing, even say classical computer, people who encode the data also have a better computer. So it's a bit like a two-player game. Sure, if I encode my data but I only do it classically, and you're trying to break my code and you have a full quantum computer, yes, I lost the game. But the reality is, also, if you have a quantum computer, then I probably have one as well. So, it's a cat and mouse game. And in some sense, it's not, in my view, related to quantum computer or classical computer. In the sense that, yes, a quantum computer, when we have a full version, yes, it will break the current versions of encoding or encrypting, but we will encrypt and encode in a different way if we have a quantum computer. It's same as these generative adversarial network or the quantum version where you have a counterfeiter and where two players improve each other by fighting against each other. So I think it would bring an end to classical internet security, but not to internet security.
Fair enough. Okay, so let's move on to the last draw for the evening before we end the session. All right, I'll just put the screen up. There it is. So, Thomas, you were the first winner. Congratulations for that. Please get in touch with me on LinkedIn, and I'll organize your free e-copy for you. So let's see who the second winner is. All the best, everyone. And Sarah Marzella, congratulations, Sarah. So, Sarah, please get in touch with me on LinkedIn or Alexei and Jack if you know them, and I'll organize your copy for you. Congratulations to both the winners, and thanks a lot for everyone for their time. And yeah, hope to see you soon. We have another episode next week. Sorry, Jack, you were saying something.
Yeah, may I just add
Yes,
one tiny thing? Well, two things actually I wanted to add. One
yes, please.
is as a personal take on all this. I think quantum
Mhm.
computing, whether you come from math, from stats, from physics, from computing, I think it's a really exciting field because to me it's actually the first time where we actually have a field which is fully interdisciplinary. Uh, and over the past 3 years, and we're building a big group in Imperial, for example, with people from physics, from electrical engineering, from aeronautics, from math, from I don't know what I forgot, computing, physics, and also with the industry, whether it's finance, whether it's pharmaceuticals, of course, quantum computing companies as well. So it's a really truly interdisciplinary field, which is really exciting and something really new to build upon. It's not just, oh, I'm solving a problem for the next 3 months. It's really to have a much, further away vision. And the other thing is, I mean, there's, thank you very much for setting that up. Of course, if anyone has any particular question or want to know more, want to discuss more, we're happy to, I'm happy to receive emails and discuss that by email.
Yeah. And also, just to inform everyone, inside the book, there is a QR code at the end of every chapter. You can join the Discord community. We have around 2,300 people on that community now. If you have any queries about the book, about quantum computing in general, or machine learning in general, you can join the community and ask us queries. And Alexei and Jack are a part of the community as well. There are other experts in there, and everyone will be more than happy to answer your questions for you and be a part of your learning journey. So, Alexei, you've been quiet for a long time. Any closing comments from you?
Yeah, so my closing comment is about the fact that quantum computing is a truly new technology. It's not just a new piece of software or repackaging of some models, some no, not it's not yet another app or something like that. It's true new technology. It's like electronics. So when electronics appeared, it was a new technology. When we started generating electricity for the first time, it was new technology. So quantum technology is similarly new technology, which manifests itself in many different areas. And now we just started to harnessing this technology because now we reached the point when we can actually do it. But we should understand that we're talking about totally new technology, and quantum computing or quantum measurement or many other things, quantum, they will play progressively more important role, especially as technology matures. So I think it's as Jack said, it's extremely exciting to be here at the very first stages uh, of this new technology that just started to sort of touch our everyday life, to sort of penetrate our lives.
Perfect. Thanks a lot for your time, everyone. Just one quick thing before we go. I can't see in the LinkedIn QR code. Lampros, what you can simply do is just click on my profile, and on my LinkedIn profile in my bio, there is a link. Join the MLEI community. Just click on that. As simple as it. Right? Cheers. Thanks, everyone. Alexei and Jack, I'll see you backstage. And thank you, everyone. Bye
Thank you
bye.
very much.
Thank you very much. Thank you.
Thank you all for coming.
Thank you.